So I went and had a walk and to get a fresh start. Actually, I'm kidding. I'm still here, sitting here, um, trying to finish off this section. You know, the good thing about using the document camera is I don't have to spend a lot of time drawing on the board and erasing, so I probably get more done. But sometimes that's a danger because you end up going too fast. Working on the board can slow you down to the speed where students can pay attention. But with using printed slides, you can easily fly through them and lose the whole class in a few seconds. So we'll try not to do that. But I don't want to have to draw these pictures, and you wouldn't trust what I drew anyway. So this you can trust because it came off a computer. That makes it trustworthy for sure. So I'm just joking. So what I did was I generated some normal data, so off of a bell curve as a density function. So how it does that is a complicated scenario, which we won't talk about now. Someday, if you took a more advanced class, they would show you how calculators and computers generate random information. It's kind of interesting, but it leads us astray right now because we're just trying to get to statistics. And that's hard enough as it is without having to talk about all the details. So here we are. If you randomly selected 100 values from a bell curve style distribution, you tend to get something like this. So you see all these jaggies like we saw with the uniform because it's random. And you see there's a humpiness to it, but it's not clear it's really bell-shaped at all. And then when you do 10,000 observations, you get a pretty clear-cut bell shape, but it still's got those jaggies on the edges. So you go, well, are those going to go away? And then the answer is sure with 1,000,000. The shape of the histogram comes up to this shape every time if you generate data from a normally distributed data set from a normal density function as your model. You get the density function shape back with 1,000,000 observations. Oh, that's nice. Look how nice that looks. So it's a bell shape, but it's a little bit different than what you might draw. These sides here seem straight, pretty straighter than you would draw. If you try to draw this, you're gonna have a hard time because it's really hard to make a hump here and then go straight for a while, straight-ish, and then curve nicely at the end. It's very hard for your hand to do that. And so when you try doing it, like I try, my pen doesn't want to do it. You try like this, and even with a lot of practice, yeah, it comes out crooked. I can get my sides kind of straight, and if I manage to get my hand centered on the page, here I'm off to the side, so my hand did something I didn't want it to do, but there you go. So sometimes people make templates of these things so they can draw pretty ones by tracing around them, or you can just practice drawing them. All right. So moral of the story is when you make a histogram with enough data, and it's a continuous situation, so you're using a density curve to describe it, you get the shape of the density curve back. Okay, and so we know about density curves, so certain things have to happen. Normal density curves we're talking about especially. So total area has to be 1. That's every density curve has to do that. They all have the same characteristic bell shape that we saw. So that shape that happens over and over again, exactly the same one. So it might be worthwhile learning how to draw it somewhat accurately. When I see students draw it, they can't even do the bad job that I do. They make things that look like turtles or triangles or World War II helmets. It's difficult to see. So to make it pointy and making it the sides kind of flat without really pointy and really flat is hard to do. The mean and the median is at the center. Well, we know that because of the balance point idea. So we said that you would try to balance the density curve and that location there to get the mean. So if it's symmetric, of course, the mean should be in the middle. That also makes sense. So the mean and median, you cut the area in half the same way. You can't see my pen. But you're cutting the area in half for the median. That cuts the area in half. Oh, you go like this, yeah. And cut the area in half. So this side and this side would have the same area. So we can look at the curve and notice where that is. True. And then we get to some more details. It says the standard deviation is the distance from the mean, the place on the axis above which the curve is steepest. Okay, so I will make another attempt here. Here's a nice level thing. It's hard to draw this because you can't see what you've drawn, but okay, we come up like this, we kind of go straight, then we make kind of a steep, and then we come down, try to make it symmetric as we can, and then we try to make this come out here like this. Well, I tried. This should actually probably come out a little bit lower, but my pen just decided to go that way. Maybe like that. That's not so bad, right? And it says the standard deviation. So to get the standard deviation, you find the mean and you look at the steepest point on the curve right there, where it's going down as fast as possible or where it's going up as fast as possible. And this distance here is the standard deviation. So what that lets you do in particular is easily mark off the axis in standard deviations like that. So that's 1 sigma away, that's 2 sigma away, that's 3 sigma away. And if you draw bell curves and you're at all like the true thing, most of the curve is gone by the time you get 3 standard deviations away from the mean. Now it looks like the curve is actually gone, but it says here, the curve gets very close to, but never touches the x-axis as x gets further and further from the mean. So if I could have zoomed in on this picture here and looked right here, there's still going to be a few values out here with 1 million observations. It's just there's so few in the picture. See, this side here is 5,000. So if there were like 10 values, you couldn't even see them. So there are some values here, but very few. And then you can see most of the values are here. In this big shaded area, there's a tiny, tiny little bit out there, which we don't care about that much, it turns out, but the graph doesn't ever, this curve that matches that, doesn't quite touch the axis as it zooms out. It's so close we don't care, but it's not quite touching. The curve is very close but never touches the axis as x gets further and further from the mean. If you take in fancy math, you'll know that would say that the curve uses the x-axis as an asymptote. So they become almost the same thing as you head off this way and off this way, but they don't become exactly the same thing. Oh, so we talked about that. All right, so more properties here. So this is more properties of normal density curves. Like that. We said bell-shaped curves or bell-shaped distributions obeyed the empirical rule. Okay, and there's 2 versions of the empirical rule. One has to do with using the mean and standard deviation of the data set. And the other one says using the mean and standard deviation of the density curve. But with these bell-shaped curves, either one is going to give you about the same results. The density curve that's exactly normal comes very close to these numbers. Density curves that are approximately normal when you have data will come close to those numbers, and says the area under the curve, or the fraction of the observations that fall from the mean plus or minus 1 standard deviation, is 68%. And then when you go 2 standard deviations, it's 95%, and for 3 it's 99.7%. So we sometimes call it the 68, 95, 99% rule, like that. The 68%, 95%, 99%, 99.7% rule, or just the empirical rule. Keep in mind the 2 interpretations of area under the curve. One, it says that area can represent proportion of the population. So you can use density curves to represent large populations, because for very large populations, when you make the histogram of them, it looks like a density curve. We saw that here with 1 million. Yeah, well, I can't tell the difference between that and a curve. It's pretty much the same thing. Or even if it wasn't, even if the population wasn't huge, you could say that it has a normal distribution. So this is just a theoretical version of where everything should be. And your population might only have 10,000 values in it or something like that. It might look like this jaggy thing here, but you could still use the curve to estimate proportions in the population pretty accurately. So it's good for that purpose. Area can represent a proportion of the population. Area also represents the probability that a randomly selected value falls in the interval. So you're picking one individual out of the population. If 68% of the values fall here, you have a 0.68 chance of choosing a person in that range or an individual, whatever type, within one standard deviation of the mean. All right, moving at light speed, it feels like. Let's see what happens next. We have to do some examples. This has to happen. Oh, look at that. We get to. Yeah, someone must have designed this so that you have to do work. Wonder who that was. So the first idea, and this avoids the embarrassment of actually trying to sketch the curve. Draw a normal density with mean 12 and standard deviation 3. So I've got here a pre-built normal curve. They all look the same shape, so that's useful. And then we just have to label the axis here. And it's conveniently already marked off in what looks like standard deviations, like this. So up above this, we find the steepest place on the curve there. And in the middle here is the mean. The mean is 12, okay. And then the standard deviation is 3. So if you go over one standard deviation, you just add 3. And then 3 more. And then 3 more. And if you go back from 12, 3, you get 9. Subtract off 3, you get 6. And 3 more, you get 3. So 3, 6, 9, 12, 15, 18, 21. Just keep adding 3 as you move to the right and subtracting 3 as you go left. And now we've drawn a normal density curve with mean 12 and standard deviation 3. That's useful just as a guide, because you could say to yourself, well, it's pretty unlikely for that kind of experiment that you see values bigger than 21. Almost 0 probability, because it's just about touching the axis. And we happen to know from the 68, 95, 99, 7 rule, so that's, what's left over is 0.3% divided in half. One half. So there's something there, but hardly anything. And if we went just to here, I wondered how likely you are to be out there. Since this from here to here is 95, there's 5% left. So 2.5% is shaded out here. And the probability then, 0.025 of it being way out there. So that tiny little bit, the chance of being larger than 18 in this situation is 0.025. 2.5% of the area is bigger than 18. So that's one thing you can do, is just quickly sketch something so you can answer some questions about, how likely do you think this is? Just gut level answer. And here it says, find the approximate mean and standard deviation for this curve. So we've taken some data here and asked a computer to fit a normal curve to it. I don't think I would have fit it that way, but that's how the computer did it, and I'm not going to fight with the computer about it. And then we know where the mean is in this case, because now we have to do some. I've got this blue pen. I'm going to mess this up. Maybe I should mess it permanently. So we need to find the middle here. So maybe that's it right there. And then we need to find the distance from the middle to the steepest part. The steepest part's like here, right? So maybe here is the steepest part. So this distance here, we have sigma here, and then we have mu there, like that. And then I'm going to zoom in to see if I can actually see what that is. So mu might be, what are these? I'm looking at what these are. It says these are 1, 2, 3, 4, 5, 6, 7 bins. I see. So it's not exactly, and we're like here, right? We're like here. We're about right around here. 3/7 of the way over. Okay, so I'm going to take, that distance is 1. So I'm going to go 3/7, 3 divided by 7 like that. and then add 1 to it, like that. So maybe 1.4, oh, add 3 to it. Add 2 more. So 3 plus 0.428, so about 343. I'll put it here. 3.43 makes sense. And then for sigma, I've got 3.43 over to just about 4. That's convenient. So 4 minus 3.43 is 0.57. So I'll go here. That's about 0.57. So we can either sketch a curve with a given mean and standard deviation by drawing a bell, labeling the center, finding the standard deviation point, marking it off in standard deviations, labeling the axis like that. Or if we have a curve already above an axis, we can look at the axis to see where the mean is. And we can go from the center over to the steepest point to measure off that distance to find what the standard deviation is. Nice. More examples, I'm thinking? Oh, damn. Oh, maybe this is the end of everything. Is this the end of the whole thing? It might be. That'd be kind of cool. I'm looking over here. Do I have more pages? It looks like I don't. This could be it for this 7 point, that's where we are, right? 7.1. I lost where we are. Oh, this is the second half. Where did I put the first half? It's gone. My density curve pages are gone, but I'll find them in a minute. Let's do these examples. Find the probability of observed value falls between 10 and 40 if x is normally distributed with mean 20 and standard deviation 10. I'm using the empirical rule. I'm going to draw the picture. It looks like this, bell curve. Pardon my lack of artistic ability. Not so bad. Mark it off in standard deviations like this. The mean was 20, 30, 40, 50, like that. 10, 0, minus 10, like that. To do it right. Mean 20, yeah, it looks like it. And then we want to be between 10 and 40. So it's all of this. Now this side should be 1/2 of 68% because it's half of the one standard deviation distance. And this side should be 1/2 of 95%. So I'm going to do 1/2 0.5 times 0.68 plus 0.5 times 0.95, like that. That should work. So 0.815 is the probability. So I could write the probability that x is between 10 and 40, like that, is approximately 0.815. And then we could ask the question, what proportion of a normally distributed population is between 10 and 100 and 200? The mean is 150 and the standard deviation is 25. What's the same calculation except a different picture? Okay, so I'll try if I see if I can draw this even worse. Here we go. Up we go, down we come, and over we go. Okay, the center is 150. And now these standard deviations are 25, 175, 200. And I go back. 125 is here. 175 is there, like that. 100 to 200. Well, that's just the two standard deviation distance. So 95%. Okay, did that. And then suppose we sample from a normally distributed population with mean 177 and standard deviation 16. Oh, well, I really think those are not very nice numbers. We'll come down here. This might work. I'll draw a slightly bigger graph because I need more room for digits, I think. Oh, a little bit lumpy. Trying my best. Here we go. 177, and then we go steepest place 2, 3, like that. and 16. So we'll take 177. We'll add 16. We'll get 193. Add 16 more. These are not nice numbers. 209. Add 16 more to get 3 standard deviations. 225. I think 177 minus 16 to get 161. Subtract off 16 more. 145. And minus 16 more. 129. So it says, use the empirical rule to try to give a range where most observations, I think most is probably 95%, and nearly all is 99.7, I'm thinking that. And so that's the plus or minus 2 sigma range, and this is the plus or minus 3 sigma range from the mean. So as here, plus or minus 2 takes you to here and to here. That's the mean. So 2 sigma is 145 to 209. That's the interval that contains most of the values. And here, nearly all of the values is in 129 up to 225. All right, so that got me through that. And I think that covers the second half of the introduction to normal distribution and density curves. We have to talk about normal scores and tables and all that, but that comes up later on. And I'm going to stop recording.